So welcome back. Next, I want to talk about Spark, the framework for call graph and call graph construction and pointer analysis. And this actually came out of the master thesis by Ondrej Lhotak, who's now a professor at the University of Waterloo. And the general idea behind Spark is that all of these algorithms that I presented, actually except for CHA, so the algorithms RTA and DTA and VTA, they can be seen as instances of one single unifying framework. And so Spark seeks to implement all of these analyses using the same methods in that framework. And then the idea is that within that framework, you can also think about which other variants are possible and thinkable, right? So Spark initially was also seen as an experimentation testbed to try out other variants that might be useful. And sometimes it might actually make sense to tweak some of these knobs in Spark to actually get analysis that are maybe a mix of some of the features of these three algorithms here, so that you get a call graph that really ideally fits your needs. The general recipe is as follows, and that's actually something that underlies all of these three different algorithms. You build a pointer assignment graph for your program, and we already saw that in particular for DTA and VTA. And then you propagate information through this graph, right? We saw that as well, this type propagation graph. And the variation actually only lies in how exactly the graph is built. So what kind of nodes does it have? In particular, that's the main variability point in the graph construction. And then what exactly is being propagated through this graph. So sometimes it can be types, sometimes it can be individual allocation sites, for instance, but we will be talking about that in detail. Let's look at what a pointer assignment graph comprises. And the kind of nodes I'm showing you here and their colors you will actually also find in Ondrej Lhotak's thesis if you take a look at this in your own time. So in the graph, there are allocation nodes, and they basically represent new expressions in your program that allocate a new object, right? And they're created for each such allocation that is contained in the program. And they actually represent a set of objects. Why not an individual object? Well, you could have such a new expression here in a loop, for instance, right? Or in a recursive call. And then whenever this expression is revisited, a new object is being created at the same statement, right? So that's why in general, it's representing a set of objects. Okay. It also has an associated type, right? So in this case, it would be type A. Okay. That's important for call graph analysis. And so all allocated objects at this particular allocation site here, they are of this type. So that guarantee we have. There can be some cases where the type is unknown, in particular when you're using reflection, for instance, in Java, like I said, then sometimes statically you can only know or figure out that something is being allocated, but not really which type is being allocated. And in Spark, this is actually represented by a special type, any type. Then also we have variable nodes, of course, and they represent also a set of memory locations holding pointers to objects in the very general case, right? That's essentially what a variable is. It's a name for a memory location that holds a pointer to an object. And this can represent local variables, but also parameters, and also static fields, and even thrown exceptions. Why are these sets of memory locations and not individual ones? Well, for instance, if you have a procedure that is called multiple times in your program, then you will have multiple instances of that procedure, right? And therefore, you will also have multiple memory locations that actually have the same name. And because we have a static view, they're all being represented by the same node, right? So for instance, if you have on your current call stack 3 instances of a method that has a parameter p, in the graph, this is being represented by the same node p, right? So we don't distinguish these different kinds of calls. This might be typed or not, depending on the setting. So there are variants of these algorithms in Spark that use typing here. Other ones do not. We'll still be talking about that. Then there are field reference nodes, and they represent simply a pointer dereference or a field access, you can say, right? So that's how they are denoted, and it has a variable node as at its base. So basically a green node is embedded here into this red node, you could say. In this case, it's P. And there can also be special kinds of field reference nodes. So for instance, if you have an access to an element of an array, then again, we don't distinguish the particular element that is being accessed. So we're not tracking individual array indices, but we are tracking the fact that some element is being accessed. And this is done through this virtual field elements and these brackets here. So this is just saying we are accessing some element in the array A, but we don't care about which one in particular. And also, like variable nodes, they may or may not be typed. So much about the basic nodes. We'll still be talking about a final class of nodes later during the propagation. But first, I want to talk about the edges that are being created. And we've already seen these earlier, basically. So first of all, there are allocation edges, which represent just any object allocation that is being assigned to a variable. So for instance, when a new hash map is being created, or in the case also where some constant, in particular a string constant in Java, is being assigned to a string variable, this is also being represented by such an allocation edge in Spark. And so you have an allocation node here, you have the respective variable node there, and an edge in between them. Pretty simple. In Suit and in Jimple, there's one particular case that I want to highlight here. So in Jimple, an allocation is always atomic and it's independent of the constructor call. So in Java source code, when you allocate an object, you have allocation and initialization in the same call, right? So you would write new hash map and then braces and brackets and basically put your constructor arguments. But in Java bytecode and also in Jimple, there are actually two different statements. So first you will have this allocation that you see here. And then in the next line, you will have a call to p.init. So this will actually then call the initializer or the constructor on the newly created object p. But here for the analysis, only the allocation is important. We don't care about the constructor call. So this is why I'm writing it such as this here. What does this edge then really mean? So basically what you see here, this edge induces a subset constraint. And this is also why this kind of pointer analysis that we have here, it's also called subset-based or inclusion-based pointer analysis. Or in the literature, you will also sometimes read the term Andersen-style analysis because Andersen is the primarily cited inventor of this kind of algorithm. And so what this edge really means is that we know for sure that P can hold objects allocated at new1. There might be different allocation edges that also point to P. This is why here we don't have an equality constraint, but only a subset constraint, right? So we only know that this is a subset of the points to set of P. So PTS is the points to set of P. It's the set of all allocation sites that P could point to. And new1 is in it, but there may be other elements in this points to set if we look at other edges. Okay. Yeah, I just said that, so that's just for you to read at home. Yeah, so like I said, why subset and not equality, right? So we can have other statements later in the program that still add other elements to the points to set of P, right? And that's why we only have a subset equation here. Also note that the analysis is generally flow insensitive. So the program order does not matter, right? So we only know that something is being assigned, but not when something is being assigned. And so that also means, let's say you have two such assignments in a row, right? Then normally by looking at the control flow, you would know that after this assignment, P is only pointing to this object, but not to this one anymore. But because we disregard the control flow here, or disregard the program order, we do not know that, right? So that's why also the subset constraints, they make sense, right? So we never override any information just by looking at any other statement. We're just adding to the information, right? So we're adding an allocation side to the points to set of P. Nothing is ever being deleted in this algorithm. Then also we have pointer assignment edges, right? So variable assignment edges. They're pretty similar, right? So here we have an assignment from P to Q, and that induces a similar constraint. So here we now know that the points to set of P is definitely part of the points to set of Q, and therefore we have this subset equation. Similarly, for store edges, right, where P is being stored to a field, exactly the same methodology, and the same for loads as well, just the inverse, not much magic here. But there is still one crucial element missing, and that I want to show to you by using the following example, which is also taken from Ondrej Lhotak. So here, let's take a look at this particular program here. So we have these allocations here, we have a couple of assignments, and then here we're actually having such a procedure call to this procedure bar. So Q is being assigned to this formal parameter S, and its field value S.F is being returned into T here, okay? So in particular, note that this object here allocated at line A2, it ends up being assigned to P.F, right? And this object A1, it ends up being assigned to Q, which ends up being assigned to S, and then to S.F, and therefore also, well, S.F is being returned here into T, okay? So if you look at the individual edges that are being produced by all of these individual statements, you end up with this graph here, right? So we have an allocation edge from this allocation here to P, okay? So that's this edge. P is being assigned to Q. Q is being assigned to S. That's here, okay? We also see that we have the same here. A2 is being assigned to R. R is being assigned to P.F. And now looking at S.F here, it's being assigned to T, all right? But we're missing something here. Take a careful look at this program. Here, we are assigning the pointer P to Q. So another way of putting this is P and Q are now aliased. There are aliases. There are two different names for the same thing, for the same object, okay? So that also means that P.F down here, which is being assigned this object, it's the same actually as Q.F, right? And Q.F in here is the same as S.F. So actually also this expression here should be pointing to A2, right? Because it's just the same object, it's just a different name for it, right? But here in this graph, we're not seeing any relationship between s.f and that object here, right? So this graph here, it's obviously missing something, right? So the problem here is that we do not yet know that P and S are actually aliases, right? We do not know that they are pointing to the same memory location. But the propagation algorithm in Spark, that will actually address this. That takes care of this. And in a few slides, I'll be talking about how that is being solved. Before I do that, I want to get back to the nodes and edges that we have described so far and show you some variants of this, because that sort of exemplifies why Spark is really a powerful framework and how it can be used to implement different kinds of analysis in Spark. You can, for example, have a subset subset-based field-sensitive analysis, like I've shown it to you here, right? So this is just the same I had on this previous slide here. But you can also have variants of this, right? So what you see here, for instance, is an equality-based analysis. So here we do not have subset equations, but we have equality constraints, actually. So where we had an edge like this earlier, a directed edge, we now have undirected assignment edges between variables. Okay, that's then called an equality-based analysis. And that's obviously less precise, right? Because, well, it makes sense why we have these, or that there's a reason for why we have these directed assignments here. Because obviously, if you assign P to Q, then Q definitely points or can point to what P has been pointing to, but not necessarily the other way around. So this here is an abstraction, but it's sometimes a sensible abstraction, because once you do that, then again you get strongly connected components that you can collapse. And Spark actually allows you to also do that. And then this can give you a smaller graph to deal with, and it can make a faster analysis. Also here, I chose to have a field-based analysis, so where we had P.F before and S.F before. This is now being represented by the single node F. Okay, that's another design choice you can make. So you can instruct Spark to just do that, and then again, you will get a slightly smaller graph. Also here, we chose an option that is called nodes for types. So instead of using single allocation nodes here, where we distinguish different objects of type O, we are now using a single node for all objects of type O. Okay, so this is now not the declared type, but it's actually a single node for all allocated objects that, at their time of allocation really point, or they are O objects. And that can be another approximation that you see here. Okay. Yeah, so you have less precision, you have a symmetric assignment relation, and that makes it more efficient, but obviously less precise. Now, when we construct this pointer assignment graph, this is done compositionally for each assignment and also method call statement. So you can really look at one statement after the other. You don't need to do it in any particular order. So in theory, this could even be parallelized very easily. There's some special treatment in Spark for some known native methods. So for instance, if you have a call to a method thread.start, if you know something about Java semantics, then you know that this will go to a run method of that particular thread or of some runnable, and Spark tries to resolve that internally so that you will see the appropriate call edges in your call graph and also in the pointer assignments. Similar to for calls to object.finalize, which go to a special finalization method. So this is being taken care of, and this can also be extended in Spark. Then Spark also implements a simplification, so it merges nodes that are known to yield equal points 2 sets, and in particular, it will collapse SCCs like we showed earlier. This is always safe to do. And then in the next step, it's actually computing these points 2 sets using the propagation, right? But this is requiring one additional element that is required because of this limitation that I showed you earlier, where we were not able to find out that certain objects are aliased. And so here we have some additional nodes which are represented in yellow, and these are actually so-called concrete field nodes. So here we do not have field of a particular type, let's say, right? But it's actually a field of a particular object. And so this represents all objects pointed to by field F of all objects allocated at the given site. Okay, so this is an allocation node here embedded into this concrete field node. And this is then a dereference of that allocation node. And this is not part of the original initial pointer assignment graph. This is an artifact of the propagation. So only during the propagation, you will be seeing these yellow nodes. Okay. And the way this is done is as follows. So most of it is pretty simple. So we just repeatedly process every assignment edge, every store and load until nothing changes. And we process allocations by generating these subset constraints like I showed you. For assignments, we're doing the very same. And then here for stores and loads, it's now a little bit different because we are generating these concrete field nodes. So in particular, when you have such a store edge here where the value of P is being assigned to Q.F, we are now doing some recursion. So we are already looking at all the allocation nodes A that are currently in the points 2 set of Q. So that's the Q object here whose field is being assigned. Okay, so we are basically listing all the possible owner objects of this field, you could say, or all their representations that we have in terms of allocation sites. And then we are creating new concrete field nodes for all these different allocation sites, right? So for each one, we're creating a new concrete field node A.F. And then P, or the points 2 set of P, is being made a part of the points 2 set of all these concrete allocation nodes. And then here at a load, we do exactly the opposite, right? So again, we list all the different allocations, excuse me, here on the left-hand side for P. And then we are creating concrete allocation nodes for them. And we are here doing the opposite assignment. And you're welcome to take a look at Ondrej Lhotak's master thesis for the concrete work list algorithm, which still implements this in a more imperative style, in case you're interested in that. Now, if we take a look at the example again, you will see that the example by this change now will actually work. So first of all, here we are propagating this allocation site to here, which means the points 2 set of P at this point now contains allocation site A1. Then we're propagating this also to Q and to S. Okay. Now the same will happen on the right-hand side. So this will be propagated to the points 2 set of R. And now the interesting case happens, right? So here we are looking at P.F, and the points 2 set of P contains A1. So we are creating a new concrete field node, A1.F, and we are adding A2, which is being propagated here, to its points 2 set. Okay, so this is basically a new yellow node that we are creating here. And now if we look at S.F, the opposite happened. So the points 2 set of S is now A1, right? So because because of this one here, right? So we have already assigned that here. And then we also have this concrete field node now, which is being recreated, right? So we have, because of s.f, we know that we now have to create a1.f again. And we now look up its points to set, right? And its points to set we have just recorded to be a2. And therefore this is being propagated down to t here. Okay. So again, we are creating the same yellow node, a1.f, you could say, and there's a match. And therefore we have this propagation that we were previously missing. So now we can find out that t is actually pointing to this object a2 here. Okay. So now in the end, I want to still talk about how points to analysis actually aids call graph construction. And I'll be doing that after the next break.